Welcome everyone. Today we're going to look into inventory optimization and more specifically the action reward, which is an idea at the heart of Lokad's quantitative approach. So first I'll give you just a few reminders about what the inventory control problem is. So the idea is that you are a retailer and you have SKUs in your inventory, and you face uncertain demand on these SKUs. You can replenish your stock by placing orders to a supplier, and your goal is to obviously optimize those replenishment decisions. At Lokad, we believe that uncertain demand must be represented by probabilistic forecasts, and the uncertainty is what makes this job so hard. If we were certain about the future demand, we could just simply adjust our stock levels to match exactly the ones of the demand we expect. But the problem is that maybe if we expect to sell 5 units, but maybe we'll sell 10, and in this case, what should your stock level be? Should it be 10, 20? Should it be 5? Well, the whole idea is to find the right equilibrium between overstocks that can generate costs and understocks that can just lead to stockouts. Because of this uncertainty, we need to choose a model and a reward function to be able to quantify those decisions. Our goal will then be to maximize the expected reward, which is basically maximize the money we make. So the model we choose at Lokad for most accounts, and it works in really most cases, is to simply define a margin. The margin is the money you'll make if you sell a unit. A carrying cost. The carrying cost represents the money that will the cost that will be generated if you were to not sell a unit in stock. So yeah, this is pretty self-explanatory. And the more subtle one is the stockout penalty. This one represents the cost that can be generated additionally to in case of stockouts. So what do I mean by that? So in case of stockouts, not only do you miss out on sales, so you lose margin basically, but also your customers might consider that this stockout is unacceptable and they will not come back anymore. So those additional costs can be taken into account in the stockout penalty. You want to penalize further the fact that you are stockout. And finally, in your model, you need to choose a probabilistic forecast of the demand. So let's take a concrete example. So this one is very simple. It's just to highlight the main ideas. So let's say that you have a highly seasonal item, so for example, Christmas lights, and that at the beginning of the season, you can place a single order that should cover all your season. You will not be able to place an order later. So at the end of the season, every Christmas light you've not sold then can be kept in stock for a year and can be sold the year after that. But you will generate this carrying cost. And the demand forecast is under the form of a probability distribution. It's just the probability distribution of the demand during the whole season. So it may look like this distribution. So this is just an example. And now you're interested in knowing, okay, how much should I order? How many Christmas lights should I put in my stock? So what you should look at is, okay, what if I order units up to a certain point K? This last unit K that I'm ordering, I'll try to compute how much money it will generate. How much more money it will generate compared to the case where I would not have bought it. So if I did not buy it, then there is a probability that the demand would have been superior to K, and then I'm missing out on a sale. So I generate a stockout penalty. On the other hand, if I chose to order it, then I have a probability of the demand being bigger than K, and then I will sell this unit, generating a margin M. So if I ordered these units and the demand was enough to have this unit sold, then there is this component, this positive component. So the probability that the demand is greater than K is equal to the area under this surface. Yeah, so basically this is the positive part of the ordering unit K. But now, if I order it, it does not mean that I'm going to sell it. Maybe if I'm not selling it, I will generate a carrying cost. So I will multiply the carrying cost by the probability of not selling it and subtract this to the previous term. So now I have an estimate of the action reward. So this is the additional reward that is generated if I choose to order this unit K. Now I can plot this, this action reward function. So here it is. So you can see that the first units you are buying, you know that you would have sold it anyway. So you generate the margin M and you avoid a stockout penalty. So you start at M plus S. On the other hand, if you order up to this point, then the last units you know for sure that you're never going to sell them. So you only generate a carrying cost. And in between, you can see how it changes depending on the probability distribution. Now, let's backtrack, and what we wanted to do was know when we should stop ordering, like how much should we order to maximize our reward. Well, this function tells us that if we order more units than this point, then any additional units we'll order will actually cost us money. So we should order up to that point. So when we cross 0, that gives us the optimal decision we have to make. So yeah, that was a pretty simple example that would that highlights the main ideas of the action reward. But in real world cases, it's never that simple. You never have a single period where the demand is nicely done and you have a single possibility of order, right? Generally, you have the possibility to replenish your inventory at generally a fixed frequency, and replenishment is never instantaneous. So you have a supplier lead time, so you need to take that into account. In order to change the model to adapt to this multi-period problem, we need to adjust the carrying cost, because the carrying cost becomes then the cost generated at the end of each period if you are holding unsold inventory. So now this is a representation of the demand in the case of the multi-period problem. And imagine that you're at present day and you want to know, okay, how much should I order now? Well, the problem is much more difficult, because you know that if you order a certain amount, you're necessarily going to sell it eventually. The question is, you don't really know when yet, and maybe you could have ordered later this unit. That's the question becomes much harder, since you need to take into account what you're going to do in the future. Let's say that I order now just enough to cover my demand up until December, but after a month, I have the possibility to reorder, but I do not do it. Then I miss out on the sales in December and January, which would be terrible, right? So this is where you need to take into account the future decisions. The problem is that, okay, how do I know what I'm going to do in the future? Well, you can't really know, right? Because the future decisions will depend on what would have happened in between, like the demand that would have been observed, and will also depend on the decision you're placing now. So this is a tricky question where you're just shifting the problem, because the future decisions you will also require the knowledge of even further decisions to be taken. So you have this this weird chicken egg problem, where you have no real way I mean, you can theoretically compute it, so you would need to consider every possible scenario, and in every possible scenario compute every single decision you should take. So obviously, the computational cost of this is way too expensive in real world cases, and we need an approximation. Hopefully, it's possible to make a very simple approximation that works very well, and this is what the action reward is based on. This assumption is that past our current decision, reordering will actually be perfect. So what does that mean? Well, it means that we can now define a responsibility window. You know that the order you place now will arrive after the supplier lead time. So anything that happens before that, it's already too late. If you have stockouts at that point or overstocks, there's nothing you can do about it. After the responsibility window, you know that you would have had the opportunity to so the responsibility window, I forgot to define it. It's the time window between the moment you receive your order and the moment you receive the next order you'll place. So whatever happens after the next order you'll place is basically not your responsibility. If there are sales happening in January, then it's not up to you to cover them. It will be up to your future you in November to cover them. And since we made the approximation that the future decisions will be perfect, then we know that these sales will be covered anyway. So how does that translate in terms of stock evolution? So let's say that you start at a given stock level. You have a decrease in stock. Remember, there's nothing you could have done anyway to avoid those stockouts. And now you place an order so the order you place now is this one. What you need to do then is cover the demand during the responsibility window. If you happen to order a unit K that is sold after the responsibility window, then you could have just delayed its order. So you will not generate additional reward for ordering it now. You will actually, so this is why you only consider the probability of selling it during the responsibility window. So we changed the formula a little bit, and then we'll have to consider the carrying cost. But this is the probability of selling the unit K during the responsibility window multiplied by the margin plus the stockout penalty, as we discussed earlier. So then we need to estimate the carrying costs. Well, for the carrying costs, the problem you have is that if you overstock now, you cannot correct it with future decisions, even if these decisions are perfect. So you need to consider how many time steps are you going to hold your units in stock, and that will give you the holding cost. So this allows us to write this updated formula. With h of key is the average number of time steps the unit K is held in stock. So you can see that at the beginning, you know that those references, those units are going to be sold before the end of the time step, so you do not generate carrying cost. Between this point and this point, then you will generate a carrying cost at the end of this time period, but not at the end of this one. On the other hand, if you go even further, then you're going to generate additional carrying costs because you're going to have remaining stocks at the end of the second period. So now that we have this formula, we can plot it. So it's quite similar to the previous example, except that we diverge when the amount, when you consider larger and larger number of units, then you will generate larger and larger carrying costs, and it never stops. because you are going to keep those units in stock longer and longer. So yes, again, you should stop whenever this curve crosses 0 to optimize your decision. Now, you may wonder, what does it look like in Envision? Then this is a simple example of code implementing this whole idea. So you just call the action reward function with a few arguments. So the 4 first arguments, I'm not going to go into the details, but they basically describe the demand forecast that you have, so that was computed previously. Then you specify the stock that you have on hand. Eventually, if you have a stock on order, you can also consider it depending on its arrival time. You also consider your lead time, obviously, and the step of reorder. The samples is just the computational power you want to assign to the precision you want on your estimation of the action reward. So then with these few lines of code, you can generate the action reward. There you find the formula I described in the previous slide, this one. And you can just plot it with this line of code, and this is what you get. Since you already had a stock, then your reward does not start does not start flat. It already decreases quite quickly, because any unit you start reordering has less and less chances of being sold. And here you see the decreasing reward, and here you can see that this tells us that we should order probably up to 47 units. So what's interesting about quantifying decisions is that it gives you tools to solve more complex problems. You could have, in the previous examples, you could have just said, yeah, but we only needed this point, right? Whatever, if the action reward function looks like before or after, we just want to know the equilibrium. Well, yes, but in real life cases, they are often much more complex than that, and you have additional constraints. So it's very nice to have a way to take into account those constraints. So those constraints can be limited budget, MOQs, or containers with setup costs. So in order to optimize your decisions, the fact that you quantified all those increments of order is very valuable. So I'll give an example here with a limited budget. So what you're trying to do here is optimize the return on investment, since your limiting factor is your investment capability. So imagine that you have quite a small budget. Then you will plot the action reward divided by the buy price, which is the return on investment. Imagine that you have 2 SKUs, and you want to know, okay, which SKU should I prioritize? By plotting these 2 plots, you can see that the SKU 1 has a much higher return on investment than the second one. So you should give it the priority if you have a small budget. At some point, however, the probability of selling this SKU decreases, and it will start to be profitable to add the second unit, because its return on investment will be higher. So here we have an example of a greater budget, where you can see that you took all the increments of order that had a return on investment superior to this limit. So that very simply gave you the optimization process needed to optimize your order, given that you had a limited budget. In Envision, what would that look like? You would have to apply the action reward just like previously, and you would have to define what's called the grid in Envision. And the grid is basically the increment of orders, you can then compute the return on investment of every possible increment of order by computing the reward divided by the cost. You can then rank those lines and just display them. So what does it look like? Here is an example. If you had only $3 to invest, what we would, this is a ranked prioritized purchase list. And if we only had $3, what we should buy is a single hat. And then the more we are able to invest, the more we are able to buy in this ranked list. And you can see that the return on investment is strictly decreasing. So whenever we stop, we know that we have optimized our return on investment given the budget we had. So this is very interesting to rank the SKUs between each other. So for example, if we stop at $51, then we can tell that we should order 3 hats and 7 hats and 3 t-shirts. So to conclude, the probabilistic forecasting requires dedicated tools because you need to define a model, you need to define a reward function, and then to optimize to maximize this reward function. And the action reward is actually a very powerful, flexible, and scalable way to do so, and is able to really tackle even more complex problems that have more complex constraints. So thank you for your attention. Check out the other Lokad TV videos. I'm sure there's a lot for you to learn there. So, thank you.